Thank you, Mr. Ayanan. Next up, can we please welcome to the stage Mr. Bin Fan, Vice President of Open Source and founding engineer of Alluxio, who will be presenting on how to architect your AI platform with optimized data pipeline.
Hello. Hello. Hi, everyone. Good morning. My name is Ben. I'm glad to be here to present our thoughts, observations in the field about building your AI platform with optimized pipeline, especially on the AI, on the data side. A little bit about myself. I'm the founding engineer and VP open source of Alluxio, and this is an open source project, so I'm the PNC co-chair. And also working in some other adjacent data or open source ecosystem like Presto. This is my email. Prior to this, I got my PhD in computer science from Carnegie Mellon. So maybe it's a little bit different from user or from the platform perspective. So today my talk is really a little bit down to the stack, that focusing a little bit more on the data side. So if you take a look in the data pipeline, what do you see data? Like where data plays an important role. So we divided this into 5 different stages. This is using a machine learning training platform as an example. And the first stage is you collect data. This is called a data collection. And then you get some data pre-processing. You need to clean the data. You need to change the data into certain formats or put data into certain stores that you like to use. And a lot of times people are using Spark or these kind of tools to do this ETL or this is cleaning. And then model training. Like people all know that this is very, a lot of people know this using open source tools like, for example, PyTorch or TensorFlow or some homegrown tools to train the model. And then you have the model and you have to evaluate the model. So there will be data involved to, the model data will be used to evaluate, and also you have certain input data to make sure this is the model you are satisfied with. And then you're serving the model. Last step, you are serving online queries and using. So basically, you can see data is involved in all these different kind of steps. So if you take a look, like what's the unique challenge? Because we are open source and we are open source data platform, so I'm a little focusing in this talk about I/O challenges in AI or machine learning jobs. Well, first of all, a lot of users talking to us, hey, Lin, I know you guys are working with analytics, like for example, with serving Spark or Presto, but can you help machine learning cases? And I was, how is that different from a traditional, not really traditional, but like the common analytics workload? A common answer is, hey, I do have a lot of files. And that is very, to me, this is actually the key difference in, or like what is unique in the AI space on the AI side, on the data side. Especially people are using photos or short video clips to train their models. That actually puts a lot of pressure. So from the user or from the data scientist perspective, you may not realize, hey, I just use different data sets with more files. But from the platform builder or platform operator's perspective, that actually adds a lot of pressure to how do I serve the data efficiently and in a reasonable cost. So it's essentially like I was talking to certain users and they're telling me, I'm training a model, and in the short run means in 6 months maybe, this model is going to cover 1 billion of small files around like 100 KB, this type of size. So that actually is a very, very hard challenge if you think about it in that way. If you have the training workloads and each training node is repeatedly requesting data and they are consisting of very small, large collection for very small files. Well, that's the first one. The second one to me is really the size of data. It keeps growing. And I was talking to, I won't name the company, but like I was in a conference talking to a, like I think it's a very well-known internet company. They're running this in the cloud. They're running their all the data platform, analytics platform in the cloud, and telling me, hey, half of my data capacity is used to store data collected last year. So the data growth is just very, it's fast and it's getting even faster each year. And this also reflects the driven factor that a lot of decisions are getting made based on more and more on data. Each companies or each platform or each product, all these decisions are getting more data driven. So we are collecting more data and we need to serve this data into our pipelines for machine learning and AI workloads. And the third is really for a lot of AI, especially AI kind of AI jobs. One key difference is it's getting more parallel compared to traditional like big data analytics workloads. It's just in nature very, very parallelable. And in that case, specialized hardware like GPUs are heavily used to train models because they can utilize the data in a very parallel way. So, for example, take an example, if you're running Spark, you're running Presto, likely you see on each node the data parallelism is on the order number of threads. It's maybe 16 or 32. So that's a very common concurrency. You see how these applications are accessing data. However, this is far more to choose from the data kind of workloads. We have seen if you're using GPUs, the data parallelism is much higher than that. Can easily achieve like a few hundred to access data in the same box at the same time. So that also creates a different challenges for how you are serving your AI workloads. Okay, so I'm just trying to simplify this a little bit using machine learning, using TensorFlow as an example, but it holds true for the entire different stages in this in the data pipelines. You can think of it more running Spark or running Presto or running some other big data tools. It's going to be the same. So a lot of times, especially for AI training, we see from time to time people are talking to us. Hey, I don't have the I don't want to build a complicated platform, and my data set is not that big. So I'm just writing my own tool, writing my script to copy this data from my maybe object store on AWS S3 or some other NFS servers. Copy this data to each local machine so they can start to run their own job. And this works when there's a startup or this is a data scope is small. But once you're covering more and more production data or you're going to serve more workloads, this is no more going to work, or it requires a full set of like a tooling to make this happen, because you have to copy the data around, that can be slow, and how you can just plan this, you can schedule this to avoid everyone gets congested. But also after training, after workloads, you also want to remove this to clean up, to reclaim the space, the storage space. Right? So it works when your data is small and when your team scale is small. But once you grow bigger in terms of both the workloads or team size, or it's going to be a nightmare. So that's one solution we see from time to time. On the data side, yeah, as I mentioned, like you do not have the direct access to the data, you have to manually copy, and once that is copied and replicated or closer to your data applications, you can achieve lower latency and high throughput because it's just closer, and you get pretty good consistent. Also, you get a consistent performance across different runs, and but in that way, you also spend a lot of time or waste a lot of time in preparing the data. Well, the other way is what we see. Take another example in the training case again, using your data directly from your original source of truth. For example, there are tools to convert S3 as a local folder in your machine, and you can using that type of tools to access the data, for example, on S3 directly, and that will work again once your scale is small. And in terms of maintenance, this is smaller because you don't have to actually do anything, right? You just configure this access layer, then you just go there directly. Well, downside is, well, good thing is you got a direct access to the data, but you have the lower latency. So you have the higher latency because you have to retrieve data repeatedly. But also, once your data is remote, we have seen this from time to time because of the company legacy reasons or because you are expanding your business, so you're trying to cover data from a remote region, from different region. Well, in that case, you get lower throughput. Sometimes it's also associated with more cost. Take one example. If you are copying data from one AWS region to another region, you will be charged on some of the API costs and sometimes the data transfer. And also you get inconsistent performance. And this really depends on whether you are sharing the network, sharing the bandwidth, but also from time to time our users told us, hey, during certain amount in certain months or certain days, and we see our network performance on AWS is bad, becomes really bad. And we get, I don't know the reason because it's black box to us, but we get someone else, heavy users is using a lot of resource from there. Same, like you don't have the good utilization for your computation, your CPU or GPU. So that's also another issue, like if you directly access the data. So as an open source project, we're building something called Alluxio, and this is incubated from UC Berkeley AMP lab. Originally, this is you can think this is a sister project for Apache Spark in maybe 8 years ago. And we were creating this open source project to make it not only work for Spark, but also work for, in general, many different platforms or computation frameworks like Presto or Trino or Hadoop, Hive, TensorFlow, PyTorch. So this is an open source project building a new layer in this data stack. We're not doing a computation, we're not building another storage engine. Instead, we're saying, hey, this is a data service you need. We call this data orchestration. And in this data service, you get first the data virtualization provides you a single point of access. So if you need to go to any address on GCP or on AWS or on your own on-premise warehouse, you can use this as more like a physical address and using Alluxio as a unified virtual address to access. We also provide the data API translation, so you can use this data platform, data service as a way, by using different data APIs to access the same set of data. You can use the Hadoop file system interface, which is super popular in Hadoop land. Hadoop, MapReduce, like Spark, or Presto, they all use this Hadoop file interface. But lately, we're seeing more and more the industry is going to the different direction, like they're going to use S3, more like S3 as a direction to use data object storage API to access data. So yeah, we also provide the S3 API. You can use the S3 API to access the same set of data, and also POSIX for a lot of machine learning tools. They're still used to use to assume there's a local folder you can just access data. So yeah, we can do that. A POSIX-like interface. And underneath of this layer, we can provide different adapters or drivers to connect to different storage services, like for example S3 or GCS or Azure or HDFS or Ceph or MinIO or different vendors they're using. And in this layer, as I mentioned, a virtualization layer to provide namespace isolation and mapping and different API translation. And in addition to that, we have our built-in distributed caching layer to provide data like on-demand and transparent data movement without users need to worry about this. So it can detect, hey, I need this data or this part of the data. We will do this data movement and data caching for you, and you don't have to do any explicit data movement or copy replication. Again, let's go back to this case. If you have this layer, if you want to do this cache, if you want to do this training, and you can just use Alluxio as a layer and exposing the POSIX API to TensorFlow, and TensorFlow can just access the object store by using Alluxio as a logical local folder and read from there, and we will cache the hot data from there, and you don't have to do anything. It provides you the near local speed to your training applications. So you get direct access, you get low latency, high throughput, consistent performance, and high CPU or GPU utilization. So this is a little bit down to the architecture. I will just be very brief from there. So essentially, this is a distributed system. This is open source, and most of these functions are in this open source. You can check it from the GitHub, and we have this we call this managed service using call it master nodes and primary master and standby master using consensus protocol to coordinate the managed service. And we have this worker nodes, a set of workloads to become this like distributed caching layer for the applications to reuse data. So this is I will be very brief on the technical details about how we implement this. This is using the local. We have this built-in storage to provide a data locality with the scale-out workers, and also the scalable masters. We're using RocksDB to store the metadata in each different master process, but also using Paxos to actually we use Redis to coordinate different master nodes to provide a consistent view. If one node is going down, we recover and fail over to a different node for the managed service for the global state. Yeah, so this is called a unified namespace, or I view this as a very cool feature that you can use this as a virtualization layer. Like in the previous talk, I think I learned from Walmart speakers that you have you have the data from different places, from GCP or from some other storage. And this is actually very common especially for a big corporation. So we see this as a lot, and this is essentially the feature that we're doing this namespace mapping. You have one address, physical address, and we can map this to you to a logical and virtual space or address. And what's more interesting is for each logical address, you can even map two different physical addresses to there. So you can use your own data policies, like for example, you want data replication, or you want to use data age-based policy to move data around. If data is warm, or is recently generated, we put it in the faster, but maybe more expensive storage, and then gradually move this to some colder, maybe some glacier storage based on the data access pattern and data age, data temperature. So that's some cool features. You can leverage the indirection in here. Okay. Sharing some case studies here. Tencent is used, this is one tech report from Tencent. They're using this for their scalable machine learning training workloads. And so they're using a 1,000 node architecture cluster to provide their robust and performance architecture to speed up the Ceph storage. Yeah, they're using Ceph for their data training, so they are having this storage data acceleration to make sure they're actually in this case it's about failure. It's about the failure ratio. So if you have too many concurrent access to the Ceph, their Ceph will be too busy to serve their training workloads. And as you can mention here, you can see here, 2.8% of jobs fail in their run-up using Ceph views. But switching to Alluxio, they see this going down to 0.73% to speed up their training workloads. Another company called Ability, and this is using, I think it's a Ceph. Actually, in this case, it's HDF, yes. So they are using this also in the middle of the pipeline, actually machine learning pipeline. They first run Spark and also Hive and some their Python tools to generate data because the data pre-processed. And right in this stage, they're writing to Alluxio as a data, like faster data layer. And then they can use this to serve the next space, which is model training to serve their training workloads. And I think in their workloads, they're having two different types of storage. I also just mentioned one. One is the object storage, which is I think it's Ceph. But they also have the remote data. Sometimes they pre-process data from a remote storage in a different data center in HDFS. So they use Alluxio to unify this namespace and using a layer as this is closer to computation. So read write faster, and you leverage Alluxio to persist the data later when the network is less busy. Yeah, so there are two cases mentioned here. One is the audio language recognition model using PyTorch, and to train on Luxio. And the other way is to use the you can see some interesting results. The end-to-end completion time for this job using their S3 fuse is over 240 hours to complete. And if you only use local SSD, of course, you need to pay the other costs, maintaining the work, maintaining the job, and you have about 60 hours. And also using a Luxio cache, which is distributed, you don't need to have a super large SSD in this case. It's also very close to it's 64 hours. And the second use case is our video portrait mapping and using PyTorch. And with Luxio, they mentioned like each epoch of the training will complete stably within 18 hours. So that's basically how they use for the machine learning pipeline. And this is the last case I'm sharing here. It's from Momo. It's you can think it's a Tinder in China. They're using this for, this is also staff, using Luxio to speed up their data access or PyTorch training on top of staff with more than 100 terabytes of data for searching and training. And in this case, they're dealing with 2 billion small files. That's a lot of files. And to reduce the metadata and data interactions, especially with staff. Okay. So in the end of the day, like this is my last slide with some takeaway. I know I was going to a lot of details, but in the end of the day, I want to a few messages I want to deliver to you. One is understand the modern data for the modern data workloads for machine learning or even sometimes for the big data analytics. We're dealing with more and more files, and we're dealing with bigger and bigger data. And the other fact is actually the newer data architecture is getting more and more separated for these two, for the computation part and for the storage part. And this is really popular because the latest Kubernetes movement and also because everyone is running their stuff on the cloud. And naturally that is how that is constructed. And now you have this decoupled workloads and decoupled architecture. You need to solve the data and I/O problem. That's the challenge we see from through every day. So we provided open source project and solution, and you can take a look and see whether this fits your data platform. So that concludes my talk. I'm happy to take your questions.
I'm not a technical expert, so I wanted to understand a little bit better. What do you mean by distributed cache? Caching layer. Yeah. So is that supported by different machines connect together?
Yes.
Each contribute a little bit to the caching?
Yeah, that's accurate actually. So if you have a single node, a single machine, I'm running this single processing machine, yeah, I can provide a cache, of course. But what if you don't have enough space, you don't have enough storage resource for the amount of data, total amount of data you're caching? Then you have to split the work across different nodes, right? And then you have to add coordination across different nodes, so they don't need to avoid, like you can avoid data replicated on each single machine, or like data A is on machine A, machine 1, data B is on machine 2. Then you can coordinate. Someone needs one data A, you can just point it to machine 1. And some other clients, or maybe multiple clients, they need data B, points to the second nodes, right? So you need this type of coordination. So you have a large collection of nodes, and each collection of nodes is contributing a little bit or its own portion of the resource, but you have aggregated capacity to serve the workloads.
Which part do you utilize? Is it the memory part or also the hard disk part?
Yeah, that's a good question. So in the early days, when we were more like a sister project for Apache Spark, we more advertising this project using in-memory resource. Like that's how Apache Spark started. Like it's in-memory processing, in-memory computing. But nowadays, actually, because we also have the capacity, we have the capability to use local SSD or local hard disk. In general, our recommendation is leave the memory to a compute. I know like Spark is very memory hungry, and also, for example, Presto or Trino, they're also very memory hungry. So and memory is also expensive. It's still a relatively more expensive workload resource to use. So I would just say leave memory, DRAM, especially DRAM, to your applications or using more localized storage like SSD. Will highly recommend, or hard disk. Sometimes hard disk can work if you have a remote data to work with.
Okay. For so many machines to work together, there could be a problem, compromised efficiency. How do we solve that?
Well, I need a little bit more context into the efficiency part. Yeah, because sometimes if you're, no matter what type of distributed system you're talking about, there will be overhead associated with many of these different nodes. Or what if one node goes down, and how do you just like stop your entire service, or this is only you sacrifice from a little bit down from your capacity or something like that, right? So these are all just very classical distributed system problems in building distributed system, right? How do you avoid a single point of failure? How do you really utilize the computing resource or storage resource or network resource well? Yeah, but like this is a very broad question. In general, yes, there will definitely be some efficiency, or I was more like overhead added to managing this large amount of machines together. Take one example, like even counting how many machines are working actively in this system, no matter it's a storage system or computation storage system, right? So a common technology you use is heartbeat. Each node, some people call this worker nodes, some people call this some other different names. Like they need to heartbeat their status, their healthiness to a coordinator or a central hub. And it works well for maybe for a couple of nodes or even a few hundred nodes. But once if you're getting to thousands of nodes, sometimes like tens of thousands of nodes, even the heartbeat itself creates a large amount of like overhead, especially to the centralized service, right? You just keep it very busy, just answering the heartbeats, right? So how do you handle all this kind of like overhead? Is definitely a very challenging problem. So I would say like any problem, if you can solve this well on a single machine, would extend this concept to a large nodes or to a distributed nodes, distributed services, or a large number of nodes. The complexity is going to be a totally next level. And yes, you have to pay extra complexity or efficiency or engineering hours to just build the machinery behind to organize them to work well. But definitely, yes, you are right. I think you have to compensate for something.
Okay, thank you.
Hello, I think this is very interesting. So when you provide open source, do you manage the caching management, provide the caching techniques to get data?
Oh yeah, we have our own. We implemented this from scratch. We're having distributed caching services. I can just go back to actually. There's one slide talking. Yeah, so we do have this distributed caching layer built by ourselves.
Okay. So you think this mechanism is optimized, or it's just based on your strategy?
So can you repeat your question?
How do you evaluate the efficiency and the optimization when you use this strategy of the cache management?
Yeah, can you? Just want to have a clarification here. Are you talking about what's your baseline? Is baseline without this? Even without this caching, or baseline is with our maybe default caching strategy? Like, what do you refer to? Are you talking about how do we prove to a user, hey, by using Alluxio, you're getting a better, or some technology like Alluxio, you are getting a better efficiency or better performance? That's what you're asking?
Yes.
Well, yeah. So this is definitely a very a key question we need to answer for when we're doing any POCs with the users, with the customers. Technically, it depends on what they are looking for. Certain users are looking for, hey, there are pinpoints, right? Certain users are bottlenecked by their, for example, their performance. I have
Так что любой,
this is
кто
very, very common. I have a slower data storage. Then I do see most of my workloads are bottlenecked on data accessing to this slower storage. So then putting this layer here, yeah, I want to measure if my query gets faster, if my training gets faster, the end-to-end performance, or even the network utilization. That's a good metrics to report, right? To check whether you get any benefits. And for certain users, they are not actually their bottleneck. So they are talking to us because they want a virtualization layer there to isolate in their data architecture. They want to isolate the computation with the environment. Environments, I mean like GCP or AWS or even their on-premise data warehouse. So they want to have isolation there, and so they can deploy this data stack anywhere. So in that case, like functionality proof is what they want. So that's basically really depends on what they are looking for.
Okay, one more question. What kind of databases are you supporting, or are you just supporting? I mean, from the database, like a.
Oh, we're not a database. We're not working with a database. Sorry, I need to clarify here. So yeah, the data applications we're supporting here is listed. For example, Spark or Presto, or like a Trino or Hive, MapReduce. It's here. It's not database. Like a database has a different, totally completely different type of data access pattern and assumption, which is not our target workloads.
Okay, so basically, apart from your platform, you have a file saver and file systems to support the data coming from, right?
File saver.
I mean, there's a huge data over there, right? So the data are saved on the hard disk.
Yeah.
And you said there's no database underneath of it?
Are you talking about, are we using any database?
Yes. Or what kind of database are you supporting? Don't you think you need a database to manage that?
No,
You don't?
we don't need a database. We build our own key value index, and database is overkill here. Like database is good. We can use database, but
Okay.
it's overkill. Like we don't need that
I
completely.
see. Okay, good. Thank you.
Does anyone else have any questions?
Thank you.